All right, so as you're working through this problem, remember what we saw yesterday, that the first step in simplifying something that looks like this is we have to simplify each of the radicals, because right now, none of them are like terms. So none of these right now could be added or subtracted because the stuff inside the square root is not the same. So this is where we're going to look for like the biggest perfect square that goes into each number, or if you're making the tree diagram, you can do it that way as well. And so for instance, that root 75 would become 5 root 3. You're going to be doing the same for every single square root before we can do anything else. All right, so when we actually go through and do that simplification, this is what each of those become. So check each, make sure you got them, all the simplifications right. Now, if you got all that part right, you've actually done, at least in my opinion, the toughest part of it. Because from here, all we got to do is add and subtract the like terms. Now, when I say like terms, that means ones that actually have the same radical in them. So like, I can add and subtract the root 3's. So I'm going to go ahead and combine all of those. So notice I have 5 minus 4 plus 3 of the root 3's. So 5 minus 4 is 1, 1 plus 3 is 4, so it's going to end up giving me 4 root 3's there. And then we repeat the same process with anything else that's a like term. I got a root 5 here and I got a root 5 here. So 5 plus 2 gives me 7. So that means I got a positive 7 root 5's there. So then this is your final answer, and that's as good as we can make it, because in order to add or subtract them, we have to have the exact same radical. So yes, they're both square roots, but one is square root of 3 and one is the square root of 5. And since they're different numbers inside, we cannot add them. It's as good as it gets. So this problem is a lot like the one that you saw come up on last night's assignment, which for some of you tripped you up a little bit. And so we're going to take some time and take a look and make sure we know how to simplify this sort. I'm going to start with actually the root 72. And you're probably wondering why, because that's the part we know well, but that's exactly why I want to start there. I want to relate it back to what we already know. So one way that you would go about doing this is making a factor tree. Now, notice I say one way. You don't have to do it with the factor tree method, but I want to show what it looks like if you are. So those of you who are doing it this way can see that you're doing it the right way, and check out some little details. So if you're doing it with the factor tree, you break everything down as far as it'll go, and then we list out all of the prime factors. That is, all of the numbers that are at the ends of branches. And I'm going to list them out in order. So that's going to be 2 times 2 times 2, because notice I have 3 2's here. And then I have some 3's at the end as well. In fact, I have a couple 3's. So I listed them all out in order, because all of those are inside of the square root. This is where we go and we start circling pairs. And so I have a pair of 2's here, which means that I can pull a 2 outside of the square root, because the square root of 2 times 2 is 2. And I can also circle a pair of 3's here, so again I can also pull out that pair. So it's going to end up being 2 times 3 on the outside. Inside is whatever was not circled, so I still have that 2 inside. And so 2 times 3 is 6, of course, so it ends up being 6 root 2. Now that's doing it with the factor tree. You didn't have to use the factor tree. You could have also just looked for the biggest perfect square that goes into 72, which is 36. If you had done it with that method, you'd write it as root 36 times root 2, and then the square root of 36 is 6, so it ends up being 6 root 2. Whichever way you do it is fine. You end up with the same answer, obviously, right? Well, we're going to use the exact same method, just with one little tweak, in order to simplify the cube roots here. So, first up, going to make some room here. So, I'm going to start by doing the cube root of 250. Well, if you do it using the factor tree method, you're going to start the same way. You're just going to start by breaking it up into all of its factors. So breaking it up into all the different numbers that multiply to give us that. And then I list them all out in order. So in this case, it's 2 times 5 times 5 times 5. Now, if you're doing it this way, the difference happens at this point. Remember, in the last one, we circled pairs. The reason why we circled pairs is because it was a square root. in this case, it being a cube root, it means we circle trios. We circle sets of 3. And so, since I have 3 5s, I'm going to circle that. Because if I take the cube root of 5 times 5 times 5, 5 times 5 times 5 is 125, and the cube root of 125 is 5. And so it becomes a 5 on the outside, and whatever wasn't circled is still inside of the cube root. So it's 5 cube root 2. Make sure you're keeping track of the fact that, yes, this is in fact a cube root here. And it's not a square root, so we got to remember to write that 3 in there. Now, of course, I said that was one way to do it. You could still use the other method too. Just instead of looking for the biggest perfect square that goes into 250, we'd be looking for the biggest perfect cube that goes into 250. Well, do you know what the list of perfect cubes looks like? Well, if not, you could always just write it down really quick. Like, what's 2 cubed? Well, that's 2 times 2 times 2, which is 8. Yeah. What's 3 cubed?
27.
3 times 3 is 9, times 3 is 27. And we can just keep on going through making that list the same way. So 4 cubed is 64. 5 cubed is 125. And just keeps on going. You basically just make that list from there. But this is all I need to go to for this particular problem because I'm looking for the biggest perfect cube that goes into 250. That is 125. And 125 times 2 gives me 250. And so the cube root of 125 is 5. And I'm left with the cube root of 2. So notice either way I do it, I end up with 5 cube root 2 for the cube root of 250. All right, so having seen that, take a moment, practice it. Please simplify the cube root of 54 on your own. All right, so when we go and do that now, we look for instance, the biggest perfect cube that goes into 54. If you're choosing to do it that way, that would be the 27. It multiplies evenly into 54. Twice. And so the cube root then of 27 is 3. So it would be 3 cube root 2. If you made the factor tree, yes, that would also work. When you listed out all your factors, you would have had 2 times 3, 3, 3. And you would have pulled out that trio of 3s. All right, so now that we got it all simplified, you've actually done all the hardest work. Now it's just a matter of simplifying by adding and subtracting the like terms. Notice what the like terms are here. I have a cube root of 2 here, and I have a cube root of 2 here, so I certainly can combine those. Can I combine a square root with a cube root? No. They would equal different numbers. The cube root of 2 is a different decimal than the square root of 2. And so we cannot combine those. So I'm going to go ahead and at least do the combining of the cube roots. So 5 plus 3 would give me 8. So I have 8 of the cube roots of 2. And since there's nothing like the 6 square root 2, I'm just going to leave it as 6 square root 2. And that's it. That's your final answer.